Every second, thousands of invisible cosmic particles pass through your body without you ever noticing. These subatomic travelers, born from distant supernova explosions, are now being harnessed in an unexpected way to monitor our changing climate. In this video, we'll explore how particle physics has converged with environmental science to create revolutionary tools for tracking soil moisture, predicting floods, improving agriculture, and even searching for water on other planets. Join us on a journey from the depths of space to the soil beneath our feet, where cosmic rays are helping us understand and respond to Earth's changing climate. Our story begins with an invisible cosmic rain that's happening right now. Every second, approximately 10,000 high-energy particles called muons pass through your body. These subatomic particles are created when cosmic rays, primarily high-energy protons from supernova explosions throughout our galaxy, collide with Earth's upper atmosphere. These collisions trigger cascades of secondary particles, including neutrons and muons, that shower down to the surface. For decades, these particles were primarily studied by particle physicists rather than environmental scientists. They were considered fascinating but largely irrelevant to practical environmental concerns. Until now, a remarkable interdisciplinary leap has occurred, applying particle physics principles to climate science in ways that few could have predicted. A breakthrough study published in the Environmental Monitoring and Assessment Journal has revealed how these quantum particles are becoming crucial tools for tracking soil moisture with unprecedented accuracy. Researchers at the University of Bristol and the UK Centre for Ecology and Hydrology have developed a system called COSMOS UK, which stands for Cosmic Ray Soil Moisture Observing System. This innovative network uses the behavior of cosmic particles to measure something seemingly unrelated: the water content in soil across vast landscapes. Unlike traditional methods that require physical sampling at specific points, this technique can continuously monitor moisture levels across several hectares simultaneously. This represents a significant advancement over conventional approaches that might only capture data from isolated locations, missing the spatial variability that's critical for understanding environmental systems. The science behind this approach is elegantly simple yet profoundly effective. When muons and neutrons from cosmic rays enter Earth's atmosphere and eventually reach the ground, they interact differently with hydrogen atoms, which are abundant in water, than with other elements in soil. As Dr. Lucy Barker, who leads the Cosmos UK network, explains, neutrons bounce and scatter when they hit hydrogen atoms in water molecules. By measuring the density of neutrons above the soil surface, we can accurately infer how much water is present below. Fewer neutrons detected means more water in the soil. The detection system consists of specialized tubes filled with helium-3 gas that capture these scattered neutrons. What makes this approach revolutionary is its scale. Each sensor effectively samples an area approximately 300 meters in diameter, providing measurements representing a much larger area than traditional point-based soil sensors. The underlying physics involves what scientists call fast neutron thermalization. Cosmic ray neutrons arrive at Earth's surface with high energy as fast neutrons. When these neutrons collide with hydrogen atoms in soil water, they lose energy much more efficiently than when colliding with heavier elements like silicon or oxygen. This energy loss process, thermalization, transforms fast neutrons into slower thermal neutrons. The proportion of fast to thermal neutrons detected above the soil surface creates a signature that correlates directly with soil moisture content. The calibration process for these cosmic ray sensors involves comparing neutron counts with traditional soil sampling during installation. Scientists take physical soil samples at various depths and locations within the sensor's footprint to establish baseline measurements. These samples are analyzed for water content using conventional methods, creating a calibration curve that relates neutron counts to soil moisture. Once calibrated, the sensors provide continuous data streams that can detect changes in soil moisture within minutes following rainfall events. This temporal resolution represents a significant improvement over satellite-based methods that might only provide updates every few days. As of early 2023, the Cosmos UK network has expanded to 51 stations across the United Kingdom, creating the world's densest network of cosmic ray soil moisture sensors. Each station transmits data in real time to central servers where it's processed and made available to researchers, agricultural managers, and emergency services. The timing of this technological development couldn't be more critical as climate change intensifies drought and flood cycles across the globe. The data collected by the Cosmos UK network has already proven valuable during recent extreme weather events. During the summer 2022 drought across Europe, Cosmos UK provided real-time data showing soil moisture depletion rates were occurring 15 to 20% faster than historical averages. This information helped water resource managers implement conservation measures weeks earlier than would have been possible with conventional monitoring systems. By detecting the accelerated drying of soils, authorities could issue water use restrictions before reservoir levels reached critical thresholds. The network also revealed surprising patterns in how different soil types responded to the extended dry period, with some agricultural regions showing resilience while others deteriorated rapidly. Professor Sarah Bentley from Lancaster University's Environment Center notes, "What's particularly valuable about cosmic ray soil moisture sensing is that it bridges the gap between point measurements and satellite observations. It gives us the perfect middle scale that's most relevant for agricultural management and flood prediction. This middle scale provides the ideal resolution for many environmental applications, filling a crucial data gap between highly localized measurements and broad satellite observations." Beyond drought monitoring, the Cosmos technology has found crucial applications in flood forecasting. Traditional flood models often struggle to account for antecedent soil moisture conditions, how wet the soil was before a significant rainfall event. This is a critical factor because saturated soils cannot absorb additional rainfall, increasing runoff and flood risk. The Cosmos network feeds data directly into the UK's Flood Forecasting Centre, improving prediction accuracy by up to 28% in specific watersheds. During the 2020 winter storms, this improved forecasting allowed emergency services to evacuate vulnerable areas an average of 4.5 hours earlier than possible with previous systems. These precious additional hours made significant differences in protecting lives and property. The continuous nature of the data stream means that forecasters can watch soil moisture conditions evolve in real time as storms approach, providing dynamic updates to prediction models rather than relying on outdated information. This represents a fundamental improvement in how we prepare for and respond to flood events in a changing climate where extreme precipitation is becoming more common. Agricultural researchers have also begun incorporating cosmic ray soil moisture data into crop yield models with remarkable results. A 2022 study in the Journal of Agricultural Science demonstrated that integrating Cosmos data improved wheat yield predictions by 17% compared to models using traditional soil moisture measurements. This improvement stems from the sensor's ability to capture the spatial heterogeneity of soil moisture across entire fields rather than isolated points. Farmers can use this information to optimize irrigation schedules, applying water only where and when it's needed. This precision approach reduces water usage while improving crop yields, a critical advancement as agricultural systems face increasing pressure from climate change. The technology also helps farmers understand how different soil management practices affect moisture retention. Cover crops, no-till farming, and other conservation approaches can be evaluated based on their impact on soil moisture dynamics throughout the growing season. This data-driven approach to sustainable agriculture represents a significant step forward in adapting food production systems to changing climate conditions. Perhaps most surprisingly, this cosmic ray technology has come full circle, from space to Earth and back to space again. NASA's Perseverance rover on Mars carries a modified version of this technology called the Dynamic Albedo of Neutrons (DAN) instrument. By measuring how cosmic radiation interacts with the Martian surface, scientists can map subsurface water ice and hydrated minerals on the red planet. The instrument can detect water or ice buried up to 1 meter below the surface, helping identify potential resources for future human missions. Dr. Igor Mitrofanov, lead scientist for the DAN instrument, recently stated, "The principles we're using to find water on Mars are essentially the same ones now being used to monitor Earth's changing climate." It's a remarkable example of how fundamental physics can address practical problems across planetary boundaries. The technology has expanded beyond Mars as well. The European Space Agency's Prospect mission, scheduled to land near the lunar South Pole in 2025, will utilize neutron spectroscopy to map hydrogen concentrations, likely in the form of water ice, in permanently shadowed regions. This information will be crucial for planning future lunar bases that might extract water for drinking, oxygen production, and rocket fuel. The next generation of cosmic ray soil moisture sensors is already under development, promising even more applications and greater accessibility. Researchers at Los Alamos National Laboratory are creating miniaturized versions that could potentially be deployed via drone or attached to agricultural equipment. These smaller sensors would sacrifice some spatial coverage, but they could be deployed in much greater numbers, potentially allowing farmers to create real-time high-resolution soil moisture maps of their fields. This democratization of the technology could revolutionize precision agriculture, making advanced soil monitoring accessible to more farmers worldwide. Another promising direction involves combining cosmic ray neutron sensing with machine learning algorithms. A team at the University of Bonn has developed neural networks that can distinguish between water held in soil and water contained in vegetation biomass, a long-standing challenge for this technology. This advancement could make the technology more valuable for monitoring forest health and carbon sequestration efforts. By understanding how water moves between soil and plants, scientists can better model ecosystem responses to climate change and improve forest management practices. As climate change accelerates and water resources become increasingly stressed, these cosmic particle detectors represent a rare bright spot, a new technology arriving precisely when needed most. They use the universe's own particles to help us understand and respond to our changing planet. The convergence of particle physics, environmental science, and space exploration demonstrates how cross-disciplinary approaches often yield the most innovative solutions to our most pressing challenges. What makes this technology particularly remarkable is that it repurposes existing knowledge about cosmic rays, something scientists have studied for decades, and applies it in an entirely new context. This kind of scientific cross-pollination is increasingly important as we face complex global challenges that don't fit neatly within traditional academic disciplines. The Cosmos Project shows how breakthroughs often happen at the boundaries between fields, where different perspectives and methodologies can combine to create something truly innovative. As we continue to face the challenges of climate change, this kind of creative problem-solving across disciplines will be essential. From the cosmic rays born in distant supernovae to the soil beneath our feet and even to the surfaces of Mars and the Moon, this remarkable technology demonstrates how fundamental physics can address our most pressing environmental challenges. The Cosmos UK network and similar systems worldwide represent a new frontier in environmental monitoring, using particles from space to track the water that sustains life on Earth. As climate change intensifies drought and flood cycles, these cosmic ray soil moisture sensors provide crucial data for water management, agricultural planning, and disaster response. The cross-disciplinary nature of this innovation reminds us that solutions to complex problems often emerge when we bridge traditional boundaries between scientific fields. By repurposing our understanding of cosmic particles to monitor soil moisture, scientists have created a powerful new tool arriving exactly when we need it most. As this technology continues to evolve with miniaturization and machine learning enhancements, its applications will expand further, helping us adapt to our changing climate. The cosmic particles passing through us every second are no longer just objects of scientific curiosity. They've become messengers helping us protect our planet's most precious resources. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.